Okay, so starting chapter 4, which is trigonometry and the unit circle. So the first things that we're starting with here aren't really going to be all that new. We've done stuff with degrees and radians a little bit in pre-calc 20, and then some of the trigonometry that we're starting out with is just a review of what we did before as well. So to start with, a radian measure, by definition in your textbook, it says that a radian is one radian is a measure of the central angle subtended in a circle by an arc equal in length to the radius of the circle. So basically what that's saying is that the radian is just the measure of an arc in a circle, where subtended just means this would be subtended. So this would be the arc subtended by this, by that central angle in the circle. So simplest definition, a radian tells us the measure of an arc length. So it's finding the circumference of the circle. This is back in grade 8, maybe grade 9 math. The circumference of a circle, formula is 2 pi r, or pi d, means the same thing. So circumference is equal to 2 pi. If we're looking at a unit circle, then the radius would be 1. So the circumference would be 2 pi. And when we're dealing with this, when we're talking about it for the purpose of formulas and finding measurements, we're usually talking about the unit circle. And anytime anything is dealing with a unit, so unit measurement, unit circle, it's 1. So the circumference of a circle is 2 pi. The circumference, of course, is going all the way around it. So if we're going all the way around the circle, we know that that is also 360 degrees. So 360 degrees is the same as 2 pi. Okay, so what happens if you don't want the whole circle? So if we only want a part of that circle, or if you think of it as a pi, just a piece of the pi, we can find out the length of the arc when we're given the degree that we're working with. So if we can see here that 90 degrees is actually 1/4 of the pi. Whoops. So 90 degrees, if we think of this whole circle as being 2 pi all the way around it. So, whoops. So if all the way around it is 2 pi, and we're taking 1/4 of that 2 pi, we're dividing it by 4, then that means 90 degrees, if we reduce this, is pi over 2, because 2 goes into 4 twice. Okay, so a full circle is 2 pi. If we're taking 90 degrees, then we're taking 1/4 of the pi, so we divide it by 4. So 90 degrees is the same as pi over 2. So 45 degrees, if this was our circle here, we've actually taken that 90 and we've divided it in half again. So if pi over 2 is 90 degrees, and we want to divide it by 2, or divide it in half, so that's the same as multiplying by 2. This is the same as pi over 2 times a half. Then that means it's pi over 1/4. So 45 degrees is the equivalent of pi over 4. 180 degrees then is half of your circle. So if a full circle is 2 pi, and we're dividing it by 2, then that means that half of it's going to be pi. So a full circle is 2 pi, half a circle is just pi, 90 degrees, so half of a half is pi over 2, and then 45, which is half of the 90, is pi over 4. So the radian measure describes the length of an arc in the circle. So the length of this arc here would be pi over 2 radians, or sometimes they're just called rads. This would be, the measure of that arc would be pi, and the measure of this arc here would be pi over 2. So to convert from radians to degrees, 90 degrees, and these should all have degrees, but for whatever reason they didn't copy into my SMART document. So 90 was pi over 2, 45 was pi over 4, and 180 was pi. And if we always start with that unit being full one is 2 pi, half of that is pi, half of that is pi over 2, and then half of that is pi over a quarter. It makes it a little bit easier to remember. Okay, so without the use of a calculator to convert from a decimal to a fraction, we can use a simple formula. So 360 degrees we know is equal to 2 pi. So to figure out what 1 degree is, then basically what we're doing is to get 1 degree on this side, we would have to divide by 360 on this side, which means that we have to divide by 360 on this side. So here we're left with 1 degree, which is what I want here. This on the right side of the equation, 2 pi divided by 360, well, those are going to cancel, and we're left with pi on the top and 180 degrees, or 180 on the bottom. The degrees is dropped off. So 1 degree is the equivalent of pi over 180 radians. So that is your formula for converting degrees to radians. So if I want to go the other direction, if I want to convert from radians to degrees, so 360 degrees again, I know is 2 pi radians. If I want to end up with 1 radian, so here's a radian and here's my radian, that means I have to get rid of that 2 pi. So I have to divide both sides out by 2 pi. This will cancel and leave me with my 1 radian. This will cancel again, but my 2 and my 360 are going to cancel, so I'm left with 180 over pi. So 1 radian is the equivalent of 180 over pi. 1 degree is the equivalent of pi over 180. Those two are not going to be on your exam sheets. You're going to be given a set of questions on your exam for this chapter where you won't have the formula sheet with you and you won't be able to use your notes, and you'll have to do the conversions from degrees to radians and also radians to degrees, and you have to remember these ratios. So the trick to it, to decide whether you're supposed to use pi over 180 or 180 over pi, is if the pi is in the question and we want to figure out, and we want to put it into degrees, so if it's a pi, it's already in radians, we want to do it in degrees, then we want to have the pi in the denominator so we can cancel. So we want to have the same unit in the denominator as we are trying to get rid of. So if we're in radians, we're trying to get rid of the radians and turn it into degrees. So that means I needed a radian in the denominator, or a pi in the denominator, to leave me with degrees only. Okay? So if we want to have something changed from degrees to radians, then that means we want to have the same unit in the denominator. In that case, it would be the degrees that we are trying to get rid of or convert from. So if I'm going from degree to radian, I need a degree value in the denominator. So that means I would use this one. So this is to go from degree to radian. This one, if I have a radian measurement and I want to find out the degree, then I'm going to have the degree in the bottom. Sorry. Yeah. So this one's degree to radian. I mixed up my words at the end. This one, if you have a radian and you're trying to go to a degree, you want the radian in the bottom. I just mixed up my last statement there. Okay. So it says radians are the form of measure we will use most in this math course, in both Math 30 or both grade 12 math classes. So let's try to use this, our formula, to find these answers. So to convert from degrees to radians, give your answer in the exact value in terms of degree or in terms of pi. So what that's saying is that you don't want to do any reducing in cases where you can't. So I have 270 degrees. So if it's a degree, that means I'm going to a radian. So that means that I need to have degree in the bottom. So that means I'm going to multiply by pi over 180. So for this one, my 270 and my 180 will reduce. 270 and 180, I can divide each of these by 90, which will leave me with 3 pi over 2. 315 degrees, if I multiply that by pi over 180, I can divide 45 into both of those evenly. So if I divide this by 45 and this by 45, it goes 7 times into 315 and 4 times into 180. So, oops, I'm trying to put my numbers together. So my conversion would be 7 pi over 4. 240 degrees into radians, multiply by pi over 180, 60 divides evenly into each of these, so that's 4 over 3, so this is 4 pi over 3. So we want to leave it in an exact value in terms of pi. So I didn't multiply through on my calculator by pi to find out what it equaled, because it won't give you an exact value, because remember there's no end to pi. Pi goes on forever and ever and ever. So the next one says, convert the following from radians to degrees. Answer exactly where possible. So for some of these, when we do that conversion and we multiply by our conversion factor, we might not have a perfect answer. It might be a decimal. So if I'm going from pi over 140, that means I'm going from my radians to my degrees. So I want to get rid of the radians, so I have to multiply by 180 over pi. So my pi and my pi will cancel. 4 goes into there once and into 180 45 times. So my answer is 45 degrees. Negative 7 pi over 3. So same thing, I'm going to multiply by 180 over pi. My pi and my pi will cancel. 3 goes into 3 once and into 180 60 times. 7 times 60 is 420, so it's negative 420 degrees. 1.57. Because there is no degree with this, there's no degree symbol on there, and this isn't a typo where it was left out, then we know that it is in radians. So this is actually 1.57 radians. Oops. So if there's no degree symbol, we know it is in radians. So that means I'm going to multiply this by 180 over pi. So in this case then, oops, that's a really bad 180. You would multiply 1.57 times 180 and then divide it by pi. And you can do that right on your calculator. Your calculators have a pi symbol, so use the pi symbol because it'll give you a more exact answer. So this one rounded would be 89.95 degrees. So another useful application of radians is that arc length. And we know that a radian is just the measure of the arc that's attended from a central angle. So when we're looking at the arc length formula, we let A equal the arc length. R is our radius. And theta is the measure of the angle. And it is always in radians. Okay, so this little symbol here is the Greek letter theta. So our formula for arc length is equal to radians times theta. And theta is always in radians. So it says a circle has a radius of 8.2 centimeters. We want to calculate the length of arc of the circle subtended by each angle. Express each length to the nearest tenth of a centimeter. So if the radian they've given me is 3.5 degrees, or sorry, 3.5 radians, so my A I don't know, my R was my radius, which is 8.2, and my theta is 3.5 radians. So using the formula, my arc length is equal to 8.2 times 3.5, and they want this to the nearest tenth of a centimeter, so that rounds to 28.7 centimeters. For example B, it is not given in radians, it's given in degrees, so that means I have to do that conversion. Since it's in degrees, I need my degree on the bottom. So 125 times pi over 180 will reduce to, each will divide by 5 evenly. Whoops. So that leaves me with 25 pi on the top and 36 on the bottom. So for this one, my A, I don't know. That's what I'm finding out. My radius was 8.2, and my theta, when I changed it into radians, was 25 pi over 36. So when you're doing this on your calculator, you have two ways of doing it. You can either do your 25 pi divided by 36 and then multiply it to 8.2, or just punch in 8.2 and then make sure you put your bracket, 25 pi, divide by 36, and then close off your bracket to get your answer of 17.9 centimeters. So the next example says determine the central angle in radians subtended by an arc of length 3 centimeters in a circle of radius 10. So this time you're going to find the angle. So they have told us that the arc length is equal to 3. We don't know what the radians is. We don't know them, or sorry, we know the radius, which is 10. but we don't know what theta equals. That's what we're trying to find out. So 3 is equal to 10 theta, so I divide by 10, divide by 10, so this is 0.3 radians is equal to theta. Okay, angles in standard position. Now this isn't a new term. We did standard position angles last year. So to be in standard position, an angle has to have its center at the origin and its initial arm along, not along the positive x-axis. So if we're thinking of our Cartesian coordinate plane, it has to be along this axis here. So it says angles can be placed in any position and still have the same value. So this one angle here, this angle here has the same measurement as all three of these, or all four have the same measurement, even though they're turned in different directions. So if they're in standard position though, they have to be in a certain spot. So when they are, an angle in standard position is viewed as the following. This side here is called the terminal arm. That's where the angle ends, terminal. If you think of terminal as an endpoint. This bottom one is your initial arm. It's the starting. It's where we start, that's where we end. The four quadrants that we're talking about is quadrant 1, 2, 3, and 4, and we talked about that in the last unit 2 dealing with the polynomial functions. If an angle has a clockwise rotation, so clockwise means it's going in this direction, then it has, the angle measurement will be negative. If it's going in a counterclockwise, so if it's going in this direction around our quadrants, then it has a positive angle. Okay, so it says plot the angles in standard position. So 120 degrees. Knowing that we're starting here at our positive x-axis, that means that we're going to go from here to the start of the first quadrant measures 90 degrees, and then we're going to go 30 degrees past that, so it would be approximately right there. So this would be 120 degrees. And when you're doing these, when you're putting angle measurements on, you should always have your little arm with the arrow here indicating which direction you're going, where it starts and where it ends. If we're doing negative 135 degrees, so negative means it has to go in clockwise position. So 0 degrees is always here no matter what. So if we're going in a negative, that means we have to go counterclockwise, or sorry, clockwise, which would be that way. So to get us to between quadrant 3 and 4 would be 90 degrees, and then I need another 45. Whoops, so pretend that's in half, right in the middle. So that would be negative 135 degrees. Okay, when we're dealing with radians, we know that this is 0, starting here, 0 radians, and if we go all the way around, it would be 2 pi. We know going 1/4 of the way was that pi over 2. 180 degrees was pi. So if I'm going 0, 1 pi over 2, this is the same as 2 pi over 2, which is just pi. So then that means this would be 3 pi over 2. And 2 pi is the same as 4 pi over 2. So pi over 6 then, to get to be pi over 6, and if I'm thinking in terms of pi over 2 here, pi over 2 to be an equivalent, to make an equivalent fraction with a denominator of 6, that would be the same as 3 pi over 6. So all I did was take my pi over 2, change it so it has a denominator of 6 so that it's the same as this. So pi over 6, I'll do this one in purple. Pi over 2 is the same as 3 pi over 6. So if this is 0, this is 3 pi over 6, and that means I would have to divide this into thirds. So, oops, that's about 1/3. So this would be pi over 6. 2 pi over 6 would be about there, and then 3 pi over 6, of course, would be at the half. I'm just going to take that one out of there. So this is pi over 6. And again, I use my little arrow on there to indicate that. Negative 5 pi over 4. So if I thought of these as all being in terms of, let me switch color here, denominators of 4, this would be 0. To be 1/2 with a denominator of 4, that would mean it would have to be 2 pi over 4, because that's the same as a half. To be a whole pi, that would be 4 pi over 4. So then that means to be the same as 3 pi over 2, it would be 6 pi over 4. So 5 pi over 4 going to the negative, this is the same as 1 whole pi, so that's a pi, and then a 1/4 pi. So going from, no, I'll do it here. So going from here to here would give me 4 pi, but I need 1 more pi, and to go all the way from here to here is 2 pi, so I need half of that to give me just 1 more pi. So that means that this would go halfway in between, and I would end right there. So that would be negative 5 pi over 4. Half of my circle is going to give me a full pi, so 4 pi over 4. I need another 1/4 pi in order to get that 5 pi over 4. So the next example says, plot the angles in standard position. What do you notice? Okay, so 30 degrees, I know from here to here is 90 degrees. So 30 degrees is 1/3 of the way, so about there. That's 30 degrees. 390 degrees means that I would have to start here, go all the way around, and that would give me 360. And then I have to do another 30 degrees, which puts me to there. Negative pi over 6. So I know from my picture on the other side that this is 0 and 2 pi. Pi over 6 was just that little bit, because if this was going this way, this is 0. This would be 3 pi over 6, or a half. So that means it's dividing it into thirds. It would be 1 pi over, this would be 1 pi over 6, 2 pi over 6, and 3 pi over 6. But I need to do this in the negative. Well, I started with the negative first, sorry. Doesn't matter. Still get you the same. Negative pi over 6 means that I have to go, whoops, that's closer to a half than a third. But I'm going 1/3 of the way clockwise. So this is negative pi over 6. 7 pi over 6 will get me to 1 full pi over 6. Here to here, this would be 6 pi over 6, which is just the same as pi, and we know that pi goes to here. So I need another pi over 6 to get me 7 pi over 6. So that would be, again, just 1/3 of the way here. So this is 7 pi over 6. So what did I notice about these? Well, 30 degrees and 390 degrees shared the same coterminal. They shared the same initial arm for this one, and it shared the same coterminal arm. They both had this little bit extra of 30 degrees. In this one here, I went the same amount past my initial or my x-axis. So this one I went pi over 6 down. This one I went pi over 6 down. So this one here, they share the same initial arm and they share the same coterminal arm. So if two angles have the same coterminal arm, means that they share the same terminal arms. Coterminal means that they share the same terminal arm. So two angles are coterminal if they share, they share the same terminal arm. So to find a coterminal angle to 35 degrees, if 35 degrees is about right there, then that means that went to here. The next one that would have the same coterminal arm means that I would have to start here and go all the way around. So what I've done is I've gone a full circle plus that 35 degrees. So I've gone 360 degrees, plus the 35 degrees. So that would be 395 degrees. So to find an angle that is coterminal with negative 9 pi over 4, you have to remember again that 2 pi is the same as 360 degrees. So what I want to do is I want to convert this so that I have a denominator of 4. So 2 pi is equal to what over 4? Well, in order to convert that, this is like saying 2 pi over 1, so I'd have to multiply by 4 on the top and the bottom. So this would be, 8 pi over 4. So I can add 8 pi over 4 onto that, which is the same as adding 360 there, which would give me negative pi over 4. In both of these cases, if 35 degrees is here, what I could do too is go in the opposite direction. I could go this way and end up with the same coterminal arm. Because remember, it has to start on that positive x-axis and end at the same spot. It doesn't say it has to go in a positive direction. So this one I could have done 35 degrees minus my 360. Which would give me a negative 345 degrees. So I could do the same thing here. I could start at my negative 9 pi over 4 and go in a negative direction or in a clockwise direction and subtract my 2 pi, or in this case, because it's a denominator 4, my 8 pi over 4, and that would give me negative 17 pi over 4. So I've given, by adding or subtracting with the 360 or the 2 pi, I can actually get 2. And you can actually get more than that the more times you go around. So how can you find a coterminal angle quickly? You just simply add or subtract 360 degrees, or if it's in radians, you add or subtract 2 pi. And you want to always change that 2 pi so that it has the same denominator as your question does. So the general solution then is basically the same thing. The only thing is you're adding an n to your formula, okay, or to your formula for the solution. And n is just the number of times you go around in the circle. So for this one here, my general solution would be 35 degrees plus or minus 360 degrees times n. And n is just going to stand for how many times I go around the circle. So in this first case, in my red one that I had here, I went around once, but I could have gone around twice. For my radian example over there, my negative 9 pi over 4, I could have added or subtracted 2 pi n and gone around however many times I want. So n is an integer. Okay, and it's just representing your rotations, how many times you go around. Okay, so your general solution when you're writing it is just going to be your theta plus, and I leave it as plus because we use the integer in here, so it could be a negative 2, which means you would be going around subtracting then. So you don't need to put the minus in there. So plus 360 degrees times n, and n is the number of times you go around. Or it could be, if you're in radians, theta plus 2 pi n. And remember, n is an element of integers. And capital Z is the symbol for integers. So instead of writing that plus or minus there, you just say you're going to use an integer. Of all the angles that are coterminal, so of all of your angles which are coterminal, which is the most important? Well, your 360 or your 2 pi is the most important because that's where you're going to make all of your comparisons to. Okay, so this next part here on the table is just for you to go through and draw them in, give 2 coterminal angles, and the reference angle is just the angle that you are doing the comparison with. So I'm going to do a couple of examples here for you, and then you're going to fill in the rest of the chart. So 45 degrees. If I draw 45 degrees, that would be halfway here. So that's 45 degrees. It's in quadrant 1. 2 angles that are coterminal, well, the simplest is just to take your 45 degrees plus your 360, and I'm only going to go 1 rotation, so it's kind of like multiplying it by 1, which is just 45 plus 360, so that's 405 degrees. Second simplest one to do is just to go 45, and then it'd be like 45 degrees adding your 360, but going in a negative rotation 1 time, so negative 1. So that's just the same as saying 45 degrees minus 360 degrees. So that's negative 315 degrees. Your reference angle then is which is the angle that you have used in order to do your comparison. So in this case, your reference angle is going to be 45 degrees. So your reference angle is always what is the angle measurement closest to the x-axis. So because this was, my 45 degrees was the measurement closest to the x-axis, then I would use 45. So 5 pi over 6. If I draw this, remember this is 0. 1/2 is, or 1/4 is up here. So if I'm using this in to go all the way around, if this is 0, that is going to be the same as, or sorry, 0 and 2 pi. So 2 pi with a denominator of 6 means I'm going to multiply top and bottom by 2, or sorry, by 6. So that's the same as 12 pi over 6. So if this is 12 pi over 6 over here, then that means that this one here, 12 pi over 6, if I half that, is going to be no, that's wrong. Sorry, I had a little pause there. No, I had it right. It was 6 pi over 6, because that would be 1 full. 6 pi over 6 is the same as pi, so that means halfway here would be 3 pi over 6. I was forgetting my denominator there, that's why. 3 pi over 6, and then this one here would be a 9 pi over 6. So 5 pi over 6 means that if I'm going to 3 pi over 6 is halfway, I need 2 more pi, so I'm going to about right here. So 5 pi over 6 ends up in quadrant 2. 2 coterminal angles would be my 5 pi over 6 plus 2 pi if I'm just doing one rotation. So 2 pi is the same as 12 pi over 6, so that's going to be 5 pi plus 12 pi, so it's 17 pi over 6. If I'm going in a negative, then I'm going to subtract my 2 pi. So 5 pi minus 12 pi leaves me with negative 7 pi over 6. Okay, my reference angle is the smallest angle between my terminal arm and my x-axis. Positive or negative doesn't matter. So that means that the reference angle is right here. And the reference angle is written as theta r. So my measure from my terminal arm to my x-axis is that little amount here. If I know this is 5 pi over 6 and I have to go to 6 pi over 6 to get to that x, that means my reference is pi over 6. So your reference angle is measure from the terminal arm to x-axis. Okay, so I'm going to leave the rest of these for you to fill in on the chart. Excuse me, and then we'll go back and correct them together. So the next one says, find the smallest positive coterminal angle with negative 5,000 degrees. Okay, so the smallest positive coterminal angle. So what we want to do is we want to see how many rotations it's going to take in order to go all, or to get to this angle. I'm just going to pause here because I have an error in my math and I don't want to. Okay, sorry about that. I just made a mistake in my math here and I wanted to correct it before I put it up on the board here. Okay, so what we want to know is how many times will 360 degrees go into there evenly. So if I divide 5,000 by 360 degrees, it's going to go 13 times, but it leaves me with the remainder. 13 times 360 is 4680. So if I take my 5,000, and you'll notice for right now I'm just forgetting about my negative sign there, but 5,000, and if I subtract 360 times 13, that's 4680. So that leaves me with 320 as a remainder. So if I do 13 times negative 360, but I'm still left with my remainder of negative 320 degrees. So negative 320 is what I'm looking at here. So negative 320 degrees is my key here. So if I go negative 320, positive coterminal angle means that if I'm going negative 320 degrees, then that means I'm going all the way this way, so that gets me to 180. This gets me to 270. And I need to go 50 degrees more to get to negative 320 degrees. So if this is 50 degrees here, to go from here, 270 to get to 320 is 50 degrees, it means that I have a 40 degree amount here. I'm left with 40 degrees to get back to here. Positive coterminal means that it has to be on the x-axis is my initial arm, and then that's my terminal arm. So I have 40 degrees. So really what I've done is I have subtracted my 320 from 360 degrees. So my smallest positive coterminal angle is 40 degrees to negative 5,000. Okay, so for my next one, 88 pi over 3. So I know 2 pi will get me 1 full rotation. So if I have my 88 pi over 3, pi divided by 3, so if I figure out how many 2 pi's are in here, so how many full pi's are in here, if I take my 88 and I divide it by 2 pi, or 88 pi, divide by 2 pi, that goes exactly 44 times. So if I take my 44 and divide that by 3, that's going to go 14 times evenly. So 14 times 3 leaves me with 42. So I'm left with 14 and oops, 14 and 2 pi over 3. No, that's wrong. Sorry. I went the wrong way. If I take my 88 pi, I started that right, and divided it by 2 pi. So that's the same thing as saying 88 pi over 3. And I'm dividing that by 2 pi to have the same denominator would be 6 pi over 3. So if I take my 6 and divide it into the 88, and where I made my mistake in the first one is I just left it as 2 pi and tried to divide that in there, but I can't forget about my denominator of 3. So this would be the same as just if you take your 88 and you divide it by your 6, that goes, if you use your calculator, go 14 times evenly, which gives you 84, which leaves you with 4. So that means it goes 14 times evenly Okay, so my 14 times my 2 pi, just like I had my 13 times my negative 360 pi, with a remainder of 4 pi over 3. So if I draw this, 4 pi over 3, if this is 0, and this is, if I'm thinking of denominators of 3, so 2 pi, this is the same as 1 and 1, or 1 and a pi over 3, so 1 full pi and a third pi, so that puts me down here. So 1 pi gets me to here, and another third pi puts me to there. So that means my smallest positive coterminal is going to be this amount here, which is just pi over 3. Okay, next example. Principal angle. To find your principal angle, it's kind of the most important angle that we're looking at. So what we're going to do, your principal angles need to be between 0 degrees and 360 if we're talking in degrees, or the principal angle needs to be between 0 and 2 pi. So what we want to do is we want to shrink that down to see what the smallest principal angle is. So we have to shrink it. Shrink down your angle. So 700 degrees, if we take 360 away, because we can't go more than 360 in there, because twice would be 320, so I subtract my 360, I always do that, 360 degrees from there, that would be 340 degrees. So that would be your smallest principal angle. Negative 1,550 to find your smallest principal angle means that you need to find how many times 360 will go into there. So if I take my 360 and see how many times it goes into 1550, well, 360 divides into 1550 4 times evenly, which gives me 1440, and leaves me with 110 degrees. Okay, But because, remember, this was going negative, then that means that this is negative. I have a negative 110 degrees left over. Principal angles must be positive, so that means I have to take it away from my 100 or my 360 degrees to find out what it would be as a positive value. So it would be 250 degrees. So my first example, because it ended up being a positive and it started as a positive, I don't have to subtract anything from it. So 25 pi over 8, if I subtract my 360 from there, so that's just going to be minus 2 pi. Well, I need to have this in with the same denominators. So I have 25 pi over 8, 2 pi. If I change that to a denominator over 8, means I'm going to multiply top and bottom by 8. So this would be 16 pi over 8. So that's 9 pi over 8. So my principal angle would be 9 pi over 8. It's positive, so I can leave it. Negative 12 pi over 7. So I need to use my 360. It has to be between 0 and 360 degrees. So each one of these so far has. So if I add my 2 pi onto here, I have to do the same thing. I have to change it so that it's a common denominator. So if it's over 7, that means that this is going to be 14 pi over 7. So 12 pi, negative 12 pi plus 14 pi over 7 leaves me with 2 pi over 7. And it's between 0 and 2 pi, so I know my answer is correct. So what do we need principal angles for? Well, basically principal angles help us to figure out what quadrant our angles are in, which for now, that's all we want to know. Once we get into the trigonometry part, which quadrant your angle is in matters for whether your answer is going to be a positive or a negative trig function. So 690 degrees, I know is between, it's not quite 2 full rotations, so I'm just going to subtract that 360 degrees from there. So that leaves me with 330 degrees. That's between 0 and 360, so that means that it's within the range of a principal angle. 330 degrees would be in quadrant 4. So 1750 is more than my 360, so I have to figure out how many times it's going to go in there and see what the remainder is. The remainder is what's going to give me the principal angle. So 360 divided by that 1750. And you would just do this in your calculator. In your calculator, you do 1750 divided by 360. It's going to give you a number decimal something. So you just take the number then. In this case, it's 4. 360 times 4 is that 1440, which we found out before, which leaves me with 310 degrees. 310 is between my 0 and 360. So I just leave that. In this example here, because it was a negative value, I had to take it away from the 360. This is a positive value, so that means my principal angle will be 310 degrees. 310 degrees is again in quadrant 4. Okay, 13 pi over 4, which means I would subtract 2 pi from there. But I need to have an equivalent fraction, so it has to be with a denominator of 4. So 2 pi to have a denominator of 4 means I multiply by 4, so that's an 8 pi. 13 pi minus 8 pi leaves me with 5 pi over 4, which is between 0 and 2 pi, so I know it's positive, it's okay. 2 pi over 4, or 5 pi over 4, puts me just over that pi. So this was 0, this was pi, So that means it's just going to be just past that into quadrant 3. Negative 17 pi over 3, so because this is negative, I'm going to add my 2 pi on there. So that means I'm going to have negative 17 pi over 3 plus the denominator of 3 means I multiply by 3, so that's 6 pi over 3. So that equals negative 11 pi over 3. Okay, but negative 11 pi over 3 still isn't a principal angle because that is still more than 2 pi because 3 goes into 11 3 times. So then I have to do it again. So if I add my 6 pi over 3, that's going to give me negative 5 pi over 3, which again is still more because it goes in there. So if I add my 6 pi on there, because this is a negative, so I have to get rid of that negative, so 6 pi over 3 leaves me with negative 5 pi plus 6 pi, leaves me with a pi over 3. So that would be in quadrant 1. Okay, another way to solve this is to pick the value that is the even number of times this would go into here. So 17 pi is close to 18 pi. 18 pi over 3 would be 6 pi. So what I could have done is taken my negative 17 pi and added 18 pi over 3 because that's the nearest whole value. 3 goes into 18 6 times. If this had been a negative, say 14 pi, then I could have used 15 pi over 3. And this still gives me the same thing, pi over 3. So I'm just looking for an even multiple. Okay, reference angle, this was in the beginning there, but the reference angle is the angle between terminal arm and the x-axis. So that was in that chart there. So it didn't have to be the positive x-axis, just an x-axis. Okay, so on your calculators, and you'll need to make sure your calculators are in degrees. If we put these in here, sine of 30 degrees, you'll notice that it equals 1/2. If you use sine of 150 degrees, you'll notice it equals 1/2. If you try sine of 210 degrees, you'll notice it equals 1/2. And sine of 330 degrees also equals 1/2. And there's a reason for this. If you were to look at angles in their standard position, so if this is 0 degrees, to go to here would be 30 degrees. Here is 90. This one here, if you were to measure this, this would be 150 degrees. Here we would have 180. This one is 210 degrees. This is 270. This is 330 degrees. So if I drew out the angles that were on that previous page, 30, 150, 210, and 330, that's where they would end up in standard position. So the one thing you might notice is the distance they are from the terminal, or from their x-axis. So 30 degrees here is 30 degrees from the x-axis. 150 degrees is 30 degrees from that x-axis. 210 degrees is 30 degrees from the x-axis. And then the last one, 330 degrees is 30 degrees from the x-axis. So all three of those angles have the same reference angle. They are the same distance, or all four of those, I mean, are the same distance from the x-axis. Their terminal arms are the same distance from the x-axis. So the difference between all of these, so the difference between the angle and the terminal arm is 30 degrees. Okay, so as I mentioned before, that theta r, and sometimes in some books they'll use the small r, means the same thing, is your reference angle. And when you're going to use your reference angle, then there is a couple of tricks that you need to know. So my reference angle here in quadrant 1, I'm going to change my color here. In quadrant 1, your reference angle was just equal to the angle. Okay, this is quadrant 1. In quadrant 2, my reference angle of 30 degrees was taking that 180 minus my whatever my angle measurement was. So in quadrant 1, in quadrant 2, to find my reference angle, I took my 180 degrees and I subtracted whatever my angle was. In quadrant 3, my angle was 210, my reference angle was 30, so 210 minus my 180 gave us my reference angle. So in quadrant 3, your reference angle is equal to the angle they give you minus 180 degrees. In quadrant 4, this is quadrant 4, my angle was 330, my reference angle was 30. Well, I know to get all the way back here is 360 degrees. So your reference angle in quadrant 4 was just your 360 degrees minus your angle. And of course you can do these with the radians too. So instead of, for these ones, instead of being 180, it would be 2 pi minus theta. This would be theta minus, sorry, not 2 pi, just pi. Pi minus theta, theta minus pi, and this would be 2 pi minus theta. So the reference angle for 500 degrees. So if I'm trying to figure this out, I need to know, okay, where is 500 degrees? Well, I need my principal angle. So I take away my 360 from here. That leaves me with 140 degrees. So I draw my 140 degrees. So this is 90 to here, so that means I need another 50 degrees, which puts me to here. So that means I'm in quadrant 2. So quadrant 2 means that I am going to take my angle, and where's quadrant 2? It's 180 minus theta. So my theta was this 140, which would be the same as going around and drawing it to 500. So if I take my theta, quadrant 2, sorry, I take my 180 degrees, I minus 140 from it. That means my reference angle is 40 degrees. So that's why I needed to know my principal angles. Principal angles just tell you the measurement from the x-axis, but your reference angle tells you the measurement to your x-axis. Or your, yeah, reference angles tell you the measurement from the terminal arm to an x-axis. So 11 pi over 4. So 11 pi over 4, if I look back to what I was doing on that other page, I have to figure out, okay, 12 pi over 4 will give me my closest one, or I can convert this into, where would that put me on my map here? So 2 pi over 4, 11 pi over 4 goes into there evenly twice. That would give me an 8 pi. So I know I'm going around twice, because here would give me 2 pi, and there would give me 8 pi. So 11 pi over 4, if I want to draw this, two full pi is going to give me 8 pi over 4, or 2 pi is the same as 8 pi over 4, so that would put me to there, but now I need another 3 pi over 4. So I'm subtracting from here 8 pi over 4. So that leaves me with 3 pi over 4, because 8 pi over 4 is the same as 2 pi. Just like here I subtracted my 360, from there I subtract my 2 pi. So 3 pi over 4 is going to put me at oops, I don't want to forget what I'm doing here. So this was 4 pi over 4. This was 2 pi over 4. So 3 pi over 4 is going to be right in there. So I'm going to go around to there. So that means that my reference angle is the difference from here to there. So my reference angle is going to be my pi over 4. So that was in quadrant 2. So quadrant 2 is to take pi minus theta. So pi minus, like if you want to do the math for this, so 2 was pi minus my theta, so my theta was 3 pi over 4, so that equals pi over 4. Okay, and then the last part. Arc length of a circle. So we already know that arc length is equal to theta times r, where a is the arc length, theta is the central angle in radians, and r is the length of the radius. So a and r must be in the same units. So if the radius of your circle is in centimeters, then your arc length is in centimeters. If it's in meters, then your arc length has to be in meters. So it says if A represents the length of an arc of a circle with a radius r, subtended by a central angle of, that should be theta, determine the missing quantity. So this one's saying r is equal to 8.7, theta is equal to 75 degrees, and A is equal to however many centimeters. So the first thing we know is that our theta has to be in radians. So I've got 75 degrees. I want it to be in radians, so that means I have to do pi over 180, because that's going to cancel out my degrees. Remember, if it's a degree in the top, then I need to have a degree in the denominator. So 75 times pi divided by 180 equals 1.3. So now I have, for my formula, A is equal to 8.7 times 1.3, so 11.31 centimeters. For example, B, they haven't given me the radius, I need to find that, but they've given me my theta 1.8 because there's no symbol or unit measurement there, then I know it's radians, and my A is 4.7 millimeters. So these are both in millimeters, so I'm okay. So if I substitute, I have A is equal to 4.7. Don't know my R, but my theta was 1.8. So I divide both sides by 1.8. So 2.6 equals R. So 2.6 millimeters. And the last one, your radian is equal to 5. You need to find your theta, and your area is equal to 13. These are both in meters, so it's just a matter of substituting. So 13 is equal to 5 theta, divide by 5, 2.6 equals theta. So 2.6 radians is equal to theta. So your assignment for these is questions 1 to 13, and they ask you to sketch them in there. You don't have to sketch them. If you want to practice that, that's okay. And questions 14, 16, and 22. And you're going to find with some of these, I stuck in the information. If you look back in the textbook, they don't deal a lot with the principal angle and the reference angle, but you need to know those things in order to find your answers for these.